Let's look at this problem in more detail and ask how can we solve it. So RNNs are intrinsically deep because when we expand them in time, when we unfold them in time, they can get deep in this dimension. And that can lead to gradient annihilation. Okay, in some learning problems, maybe we have short time dependencies. Let's say we want to predict a word in a sentence, so we want to complete a sentence. The clouds are in the sky. That's a short sentence. So our prediction output doesn't, in order to predict the correct output, we don't need to look at too many things back in the past. If we say encode these letters or words in the previous time steps of the input. Okay, but we could have very long time dependencies. So for example, we have these sentences. I was born in France. Over the years, I have learned many foreign languages, but my native language is, and then the correct output should be French because I was born in France. But I have to go back quite a lot, a long history. So my network has to become quite deep in time in order to be able to make the right predictions. And then we have this problem of gradient annihilation if we have non-linearities at every time steps here. So what can we do? Let us look at this in some more detail. So this is a time unfolding of a simple RNN. That is basically what we have seen before. We have inputs x, outputs. In this case, we just look at the hidden variables h. We will then maybe predict the output variable o, but let's just stop at h at this point. And we will update h based on the previous hidden variable ht minus 1 and the current input xt using some linear transformation and then going through a nonlinearity such as tan h. And if we unfold this network in time, we have to go through this tan h here many times. So that is the problem. That is what kills the gradient. And we have to avoid this. And so the first RNN structure that could avoid this was the long short time memory LSTM proposed by Hochreiter and Schmidhuber as early as 1997. So this was an extremely innovative but also very complex network architecture and is still used very, very much. So this is an extremely successful neural network architecture. And the idea is the following. We will look at this quite complicated architecture in more detail in the next slides. But the idea is that instead of just going through these nonlinearities in time, we have two pathways here, the lower and the upper pathway. And the upper pathway is the so-called conveyor belt, and it undergoes only linear modifications, multiplications and additions. And this pathway goes deep in time and it can carry gradient information deep. It doesn't go through any nonlinearities, so it doesn't suffer from the gradient annihilation problem. On the other hand, the modifications we make to this pathway are nonlinear. So there's a nonlinear control logic here. We have to have nonlinearities, of course, because otherwise there would be no point in going deep. Otherwise it would just be essentially a matrix multiplication. But that is all essentially in the second pathway. So that is the main trick of LSTMs, and now we will look at what these individual components do in detail and why they were chosen as they were. Now let us look into detail how the LSTM works. As I mentioned before, the core idea is that we have the so-called conveyor belt or cell state which carries information deep. We call this variable CT, so it's also some array or tensor, and we have it for every time step. So we have t minus 1, CT minus 1 before, and CT after an LSTM cell. We only make linear modifications of it, and therefore this carries an internal information. It's some sort of hidden variable deep into time. Now this avoids gradient annihilation, so that's a key aspect of the LSTM. But now we have to change the information in the C variable in every time step. We have to remove and add information, and we do this by so-called gates. These are basically neural versions of logic gates, and they regulate which information passes into the cell states. And for them, we use generally sigmoid layers, so layers that have output activations between 0 and 1. And we make a lot of use of pointwise multiplication, because then we can basically make selections. So we can zero out certain variables by multiplying them with 0, or we can keep them by multiplying them with 1. Okay, so what components do we have in such an LSTM cell? Now the first component is the so-called forget layer gate, or the forget gate layer. What does it do? It decides whether to keep or discard part of the cell state based on the current input xt and the previous hidden variable ht minus 1. Right, we have two hidden variables here, h and c. We keep the name hidden variable for h, and c is called cell state. Okay, this part is supposed to allow us to forget something in the cell state. How does it do that? Well, we have these inputs into the forget gate, ht minus 1 and xt. We work with some linear parameters, w and b, that we learn, put it into a logic gate, so a sigmoid gate, and that is the output of our forget signal. The forget signal basically says if it's 1, just keep this corresponding dimension or variable, and 0 means forget this dimension in the cell state. So as an example, let's say we train a RNN, an LSTM RNN, on word-based text prediction, and we have a cell state or part of a cell state that encodes the gender of the current subject that we have previously read, so that we can, for example, use the correct pronouns in an output. But now we see a new subject in the current time step, or the current word. And then we need to update the gender. So first we need to forget the gender of the previous subject. Okay, so that's the forget gate. Now we want to update the cell state. We want to learn or add some new information based on what we have currently seen as an input xt. And for that we have the preparation of the new cell state, which again depends on ht minus 1 and xt. And we have two parts here, the signal it and ct tilde. And it is again a logic state. So we have a sigmoid nonlinearity in order to decide which values of the cell state will be updated. Whereas the value that is used for the update, ct tilde, is using a tan-h nonlinearity here. Yeah, that is, you can choose other nonlinearities here. The idea is that this is not a logic gate. So this is actually the preparation of the content that will be written into the cell state. Okay, so this is made for updating certain pieces of information that we might just have forgotten using the previous forget gate. So for example, in the word-based text prediction, we want to adopt the gender of the new subject in the cell state in order to replace the old one we are forgetting. Now we need to update the cell state based on the forget gate and the preparation of the update of the cell state. And we do this as following, using this linear operation. So we take the forget outputs and multiply them with the previous cell state, and we add the new cell state, but we select the variables or the parts of it that we want to update. So if these forget and new cell state gates go hand in hand, the forget gate can select certain pieces of information in the cell state that will be erased, and the update gate will select the corresponding updates with new values and insert new values into the cell state. So we have the forgetting and the adding of new information. And the example again, we have the word-based text prediction, and we now drop the information about the old subject's gender and add the new gender. Okay, and the last part of the LSTM is the output and the preparation of the new hidden state. So first of all, here we have a relatively simple output function. We simply take the current hidden state, or the previous hidden state. This is still called h-1 here. We have some linear modification, put this through a sigmoid function again, and output this state. So this is, for example, useful for classification. We get outputs between zeros and ones if we do this. But we can further append other transformations, other nonlinearities, a deep network, if this is not what we want. Okay, but so this is called the output signal O of t. And now we update the hidden variable again. And now there's an important step. We take our conveyor belt state, the cell state C, and together with the output O that we have just prepared, we feed that back into the new hidden variable ht using a nonlinearity. If we wouldn't do that, our cell state would just be deep and linear. But now we feed this deep information that is carried in the cell state back into the hidden variable. So the hidden variables can benefit from the fact that the network is deep in time. Nonetheless, the modifications of the cell state always stay linear, so they do not suffer from gradient annihilation. But in the next time step, the cell state will be again modified non-linearly. Well, it will be modified using linear operation, but using a nonlinear control logic which depends on the hidden variables, which just have been nonlinearly updated using the cell state. So this means we can do complex updates of both C and T in every time step, but we still retain the benefit of having no gradient annihilation in C. Okay. Okay, so here we just generate an output. So let's say word-based text prediction, we just saw a subject, and now we want to output some information about it. For example, whether the subject is singular or plural, so that we can know what form of the verb should be conjugated or what follows next. Okay, so let's just look at the whole structure of the LSTM again in its whole complexity and beauty. And although many other recurrent neural network structures have been proposed, this is essentially the first RNN structure which solves these fundamental problems of having difficulties to train deep in time. And it's really an extremely innovative and brilliant invention. Because it has very early in time solved two fundamental problems that were in some sense rediscovered later in other architectures. So one is, how do we carry gradients deep in time? Well, we have a pathway on which we just do linear modifications using some nonlinear control logic. And that is exactly what is done in ResNets much more recently. So ResNets have come up in, I believe, 2015. And that is the state-of-the-art architecture to train feed-forward neural networks or convolutional neural networks deep in the input-output dimension. But this has already been anticipated here in LSTMs. Another aspect that is present in LSTMs is this control logic, where we decide which of the variables we want to update, for example, using the forget gates or the update gates. And this is essentially some sort of self-attention. And self-attention is key in current state-of-the-art architectures to work with sequential data, such as in language-to-language translation, for example. So transformer networks is the current state-of-the-art architecture. To do this in transformer networks, excessively make use of self-attention. So these are two extremely important aspects which explain why the LSTM is so useful and is still used a lot today, despite the fact that it's more than 20 years old, and it's really been an architecture that was a lot ahead of its time.